Hi everyone, in this video we're going to be discussing what determines molecular shape. The main determining factor of molecular shape is of course the VSEPR theory. And what does VSEPR stand for? It stands for valence shell electron pair repulsion. Now we know that electrons exist in pairs, okay? And if we're talking about a molecule, then we're talking about electron pairs around a central atom. And these electron pairs are going to find the maximum distance away from one another in space, in three-dimensional space. And the reason for that is simply because they're negatively charged, and so they're going to repel one another, those like charges. So electron pairs can either be lone pairs or non-bonding pairs of electrons, or they can be bonding pairs of electrons. So they are shared within the molecule, between the atoms of the molecule. So we're going to look at what the molecular shape of a molecule is going to look like when it has 2 electron groups around the central atom, 3 electron groups around the central atom, and 4 electron groups around the central atom. So if we start with, and the central atom is going to be denoted by the letter C, just for ease. So if we look at just a sample molecule that has 2 electron groups around it, it is always going to be, and just bearing in mind, the number of lone pairs that it has is 0, okay, so all of the electron groups are involved in bonding. It is going to have a linear shape. Now, an example of a molecule with such a shape is carbon dioxide. So it's got 1 electron group and another electron group, okay, so they're 2 pairs of bonding electrons on either side of the carbon, and it is going to have a linear shape. Now, you can imagine if any of these groups of electrons were lone pairs, okay, one of the groups was lone pair, it would still be linear, okay? So we are not going to worry about filling out the rest of that column. Let's move on to what happens if we have 3 electron groups around the central atom. So that would look something like this, and that is what we call a trigonal planar shape, okay? An example of that one is boron trifluoride. Okay, and boron is a bit of an exception to the octet rule where it is actually stable with the 6 electrons surrounding, or with the 6 electrons, okay, instead of 8. So it falls into that category of an exception to the rule, and it also is a trigonal planar molecule. Now, I'm just aware that this is not lining up correctly, but if we had one of those electrons be a lone pair, like what I'm doing here with the C, and this is the lone pair of electrons here. Okay, this now, you can see that the shape of the molecule becomes a bent shape. Okay, so any molecule that has 3 electron groups with one of the electron pairs as lone pairs, it is going to have a bent shape. And let's go through to the 4 electron groups now, because a lot of what we're going to look at in terms of the molecule is going to just derive from having 4 electron groups and then the different numbers of lone pairs. So if we have one central atom and the 4 atoms surrounding it, which are all bonding pairs of electrons, so we've got 4 electron groups, then this is going to be what we call a tetrahedral shape. Really nice example is methane, which we've looked at a few times now, and that is carbon with the 4 hydrogens surrounding it. Okay, just so we know, okay, because this is 2-dimensional, in 3-dimensional space, these electron pairs are 109 degrees apart, the bond angles. If we then move on to what happens if we replace one of those bonding pairs of electrons with a lone pair, then it's going to look something like this. Oops, and I've just used the hydrogens there accidentally. I'm just going to use our key and make those X's. We call this a trigonal pyramidal. Okay, you can see that it is, quite a pyramidal shape if we drew a pyramid around it. And our quintessential example of this molecule is our nitrogen with the 3 hydrogens, which is ammonia. And the approximate bond angle between these is actually a little bit closer, 107, between the bonding pairs of electrons, because this electron cloud of the non-bonding pair actually pushes these bonding pairs together. Last but not least, if we had a central atom with 2 lone pairs of electrons, okay, that is also, you can see a little bit of a similarity here between this molecule and now this one here. It is also going to have a bent or an angular shape. And again, our common example of that is water. Okay, once again, I'll just briefly show you the bond angle is around 105 degrees, okay, because again, these lone pairs of electrons take up a lot more space. Their electron clouds take up a lot more space, okay, because they're not kind of reined in by any nuclei on either side of those, and then they are going to repel and push these bonding pairs of electrons closer together. Okay, so that is what we need to know for molecular shape. So we have linear molecules, we've got trigonal planar molecules, we've got bent molecules, tetrahedral, trigonal, pyramidal, and bent. Okay, and that's going to help us to understand the impact of polarity on molecules as well. Okay, so I hope that you found that useful.